So I'm going to be looking at extinction geography and the sampling of marine invertebrates at the Cretaceous-Paleogene boundary. I'm aiming to look at the kind of effect of things like latitude and other indicators of how widely spread taxa are on the survival. And then I'm also looking at how sampling can affect the apparent severity of the extinction. So to do this, I've got downloaded data from the paleobiology database, and this is data on 7 different marine invertebrate taxa from the Maastrichtian and Danian ages. I know this looks like a lot of graphs to look at all in one go, but essentially the x-axis for all of them is the total number of paleocontinents that those genera occurred in, and the y-axis is the probability of survival at the extinction boundary. So as you can see with the paleocontinents as a kind of indication of how widely spread the taxa are, the higher number of paleocontinents, the more likely they are to survive, and this is fairly consistent over all of the groups. You can see with the bryozoans it looks a little bit odd. I think, to be honest, that's more of a sampling issue. There was very few occurrences in the paleobiology database for the bryozoans, but other than that, they're all fairly consistent, and you can see the graph at the end with the all the data combined for the 7 groups. It's still showing the same patterns. So then I went on to look at the latitudinal range, and again this is used as an indication of the how widely spread the taxa are. And again, it is a lot of graphs, but the x-axis for all of them is the range of the latitude, and the y-axis is just the probability of their survival at the boundary. And again, it makes a lot of sense that the taxa that have the widest ranges are the ones that were most likely to survive. And again, there's really consistent results for all of the different groups. So then I went on to look at the hemispheric differences between the north and the south hemisphere, and how that affected the survival. And when you combine the data for all the 7 groups and look at them together, the percentage survival was higher in the southern hemisphere than it was in the north. And this is the same for the gastropods. However, with the bivalves, it's actually the opposite, and the higher percentage survival was in the northern hemisphere. Again, there you can see that with the taxa that occurred in both hemispheres, they were the most likely to survive. They had the highest percentage survival. So this is indicating that the things in most hemispheres are most likely to be those with the larger geographic ranges, and those are the ones that are more likely to survive. And you can also see when you're looking at this data that the south is actually fairly underrepresented. And I think this is possibly, there are a lot more paleontologists in the north, and I think a lot of work has been done in the north, but there's kind of this problem that there could be loads of data in the south that no one's really doing anything with. So this kind of leads me on to talk about sampling. So again, sorry, I have lots of graphs on one slide, but the main graph in the middle, this is showing the data combined for all of the 7 groups of invertebrates that I was looking at. And you can see that if you increase the amount of sampling before the extinction in the Maastrichtian, then the extinction rate appears to be higher. Whereas if you increase the amount of sampling after the extinction, then the extinction rate appears to be less severe. So essentially, this is that the more things that you sample before the extinction, you're finding the more sampling that you do, you're more likely to find the rarer taxa that you didn't find, the first time around, and the rare things are more likely to go extinct. So this kind of makes sense that the more sampling you do, the worse the extinction appears before the extinction. Whereas when you're sampling in the Danian, everything that you find is another survivor. So the more sampling you do, the less severe the extinction appears. You can also see that the effect of the sampling in the Danian has a bigger impact, so there's more of a difference in the extinction than there is for the Maastrichtian. And this is because in the Maastrichtian there's quite a lot of data, and each new thing that you find is just kind of one extra bit within everything. Whereas in the Danian there's a lot less data, so each new thing that you find has a much bigger impact on the kind of overall picture that you're seeing. I've also, and these heat map graphs, also the with the littler graphs around the outside, you can see that the patterns are again fairly consistent over all of the groups looked at. But if we concentrate just on the combined data, I can understand that these graphs can be a little bit complicated to look at, so I've also produced some of the more kind of traditional graphs. And you can see that this the lower graph here is showing the Maastrichtian data. So again, you know, it's showing that the more sampling you do, the more severe the extinction appears. Whereas in the upper graph here, looking at the Danian data, it's the opposite, where the more sampling you do, the less severe the extinction appears. And you can see, comparing these graphs together, that the Maastrichtian one is a lot less of a gradient, because it's having less of an impact with the amount of sampling that you do, whereas the Danian graph is a much steeper curve, because there's a really big impact by every new sample that you find. So to conclude, the kind of looking at the geographic range by looking at the latitude and the paleocontinents, you can see that the things that have really large ranges are much more likely to survive the extinction compared to those that have smaller ranges. And again, if you're looking at it in terms of the hemispheres, those that occur in both hemispheres are more likely to survive because they're more likely to be widely spread. And the amount of sampling that you do after the extinction has a really big impact on how big the extinction appears to be. And I think this is a really important thing to take into account when you're looking at the overall extinction rate. These are the references that I've used, and here are some acknowledgements. James wrote the R code for the heat graphs, Nick, my supervisor, and Tim and everyone in the paleobiology lab for their help and advice. Thank you.